Stanford University.
General relativity, GR. For some reason that I don't know, special relativity is never called SR. General relativity is often called GR. My guess is a good many of you know a little bit about general relativity, but I'm starting at the beginning. And my own taste in the matter is to start pretty much where Einstein started. It's not that I can't get past my love affair with Einstein. It's not that. It just seems to me the right way to approach the subject. To begin with the equivalence principle. Begin with the basic, simplest facts. You know, I probably said this before, but it was a pattern of Einstein's thinking to start with a really, really simple elementary facts that almost a child could understand and deduce these incredibly far-reaching consequences of them. And personally, I think that's the way to go about teaching it, to start with the simplest things and deduce the consequences. So I will begin with the equivalence principle. What is the equivalence principle? The equivalence principle is the principle that says that gravity is in some sense the same thing as acceleration. So we want to get that on the table, say what it means, give an example or two about how Einstein used it, and then go on from there to asking what kind of mathematical structure does a theory have to have in order that the equivalence principle be true? What are the kinds of mathematics that have to describe it? I'm sure most of you know that general relativity is a theory not only about gravity, but it's a theory about geometry. So it's kind of interesting to start at the beginning and ask, what is it that led the man to say that gravity has something to do with geometry? Okay, so gravity equals acceleration. What does that mean? And I'm going to take you back. We're going to go through a very elementary derivation of what that means. It's not that this derivation is important, but it's worth formalizing. Formalizing means making equations that say the words. You all know that if you're in an accelerated frame of reference, an elevator accelerating upward or downward, you feel an effective gravitational field. Children know that because they feel it. You know that. You can probably even explain to me why that's true, but it's worth making a little bit of, it's sort of overkill, but making mathematics out of it, and then seeing what that mathematics is talking about. Okay, so let's imagine the Einstein thought experiment. Somebody in an elevator. The elevator got promoted to a rocket ship in later textbooks, but I've never been in a rocket ship. I have been in an elevator, and so I know what it feels like to be in an elevator. And let's think of an elevator. An elevator is moving upward. It may be moving downward, in which case this velocity vector here is negative. But let's draw just a velocity vector. This is not a cable pulling it up, or it could be a cable pulling it up, but it's just a velocity vector. Okay, the velocity vector is up. And there are two coordinate frames. One coordinate frame is at rest on the Earth, and let's call it Z. I use the Z coordinate for the vertical coordinate of space, and down here someplace is Z equals 0. Could be the surface of the Earth, doesn't matter. Now, in the elevator, there's also a coordinate system, and that coordinate system is being measured. This is arbitrary, but we'll do it anyway. It's being measured from the floor of the elevator, and so the same physical point, let's say it's a point over here, has a Z coordinate and it has a Z prime coordinate, and Z prime is measured from the floor. Now, the height of the floor of the elevator. The floor of the elevator, its height relative to Z equals 0, let's give a name, let's call it L. And L is clearly a function of time. We're going to be interested in the following question. If we know the laws of physics in the frame Z, surely we can figure out them in the frame z prime, and we're going to do that. Now, one warning, not warning, but one fact about today's lecture. At least in the start, I'm going to ignore special relativity. This is tantamount to saying that we're pretending that the speed of light is infinite, or we're talking about motions which are so slow that the speed of light can be regarded as infinitely fast. In fact, you might say, if general relativity is the generalization of special relativity, how did Einstein get away with starting thinking without special relativity? And the answer is something like this. Special relativity has to do with very high velocities. Gravity has to do with heavy masses. There's a range of situations where gravity is important, where high velocities are not. So Einstein started out thinking about gravity for slow velocities, and then combined it with special relativity to think about the combination of fast velocities and gravity. And that's the general theory. But let's see what we know just from slow velocities. Okay, let's begin with inertial reference frames. Let's suppose that z prime, both z and z prime, are inertial reference frames. That means they're related by uniform velocity. Uniform velocity. And that means that L of t can just be taken to be vt. The height of the elevator relative to the floor, relative to the, not the floor, but the relative to the ground, is just given by a uniform velocity v times t. I've chosen the coordinates such that at t equals 0, they line up. At t equals 0, both z and z prime are equal to 0. And now the elevator is rising, and the height is proportional. The height of the floor is proportional to vt. And then we can write down what the connection between z prime and z is. Z prime, this distance, is just z minus L. Now, L is a function of time. So it's z minus L of t. If we know what L of t is, this is a kind of coordinate transformation. What about t prime? What about time in the elevator? We also ought to ask how time behaves in the elevator. If we're going to forget special relativity, then we can just say t prime and t are the same thing. We don't have to think about Lorentz transformations and that sort of thing. So the other half of the coordinate transformation would be t prime is equal to t. They're just the same thing. And finally, we could also put another coordinate in here. Later on, we'll be interested in the coordinate x going this way. There's also one coming out of the blackboard, y. And as long as the elevator is not sliding horizontally, then x prime and x can be taken to be the same. It's true, I've sort of offset the elevator relative to this axis, but I didn't have to do that. I could have put the z-axis right down the middle here, in which case I would say that x prime is the same as x. That's a coordinate transformation. It's a coordinate transformation of the space-time coordinates. It's rather trivial. Only one coordinate, namely z, is involved in any interesting way. We can, if we like, put a prime here because t prime and t are the same thing. Okay, now, if I set L of t equal to vt, then this is very simple, minus vt. Good. Now let's ask about a law of physics. Let's take the law of physics, Newton's law of motion, F equals ma. And what is A? A is z double dot. The second time derivative of z with respect to time. That's called the acceleration, the vertical acceleration. This, of course, is the z component of force. Let's forget about the x component of force and the y component of force. They're not interesting in this context. Whatever force is exerted, now this is the formula in the z frame. This is z. We can imagine in the z frame that there are forces acting on a particle. This could be a particle over here. There are forces acting on it. What do those forces do? Well, there could be some charge in here exerting forces on a charged object in here. It could just be a force due to a rope hanging the particle from the ceiling. Any number of different kinds of forces could be acting on the particle over here. And we know that its equation of motion in the original frame of reference is just F equals mz double dot. What is the equation of motion in the primed frame? Well, this is very easy. All we have to do is figure out what the original acceleration is in terms of the primed acceleration. What is the primed acceleration? The primed acceleration is obviously z prime double dot. And z prime double dot, the z prime acceleration, is just gotten by differentiating this twice. But if I differentiate vt twice, I get nothing. It's linear in t. Differentiate it twice, you get nothing, and you simply find z double prime, z prime double dot is just z double dot. The acceleration in the two frames of reference are the same. Now, I know you know this. I know you know all about this, but I wanted to, sort of formalize it to bring out some points, in particular, the point that we're doing a coordinate transformation, and we're asking how laws of physics change in going from one frame to another. So now, what can we say about the Newton's law in the primed frame of reference? Well, we can now just substitute. F equals m z double dot prime. And what do we find? We find that the law, Newton's law, in the primed frame is exactly the same as Newton's law in the unprimed frame. That's not surprising. They're moving with uniform velocity relative to each other. If one of them is an inertial frame, the other is an inertial frame. Newton taught us that the laws of physics are the same in all inertial frames. So that's a sort of formalization of the argument. Now let's go to an accelerated reference frame. An accelerated reference frame, L of t will be increasing in an accelerated way. And so an accelerated way would be to put here 1/2 the acceleration times t squared, excuse me, and let's call the acceleration g, little g, for obvious reasons. Okay, let's call the acceleration little g. If you don't know what the obvious reason is, you'll find out in a minute. All right, now this is a uniform acceleration. If I differentiate L twice, the first time, let's do it. If I differentiate it once, I get L dot, and that's just gt. Notice that this says that the velocity of the floor increases with time. It's not steady velocity. And L double dot, is just equal to g. So this elevator is uniformly accelerated upward, and the equation connecting the coordinate transformation now is different. It's minus 1/2 gt squared. So that's my new coordinate transformation to represent the relationship between coordinates which are accelerated relative to each other. I'll continue to assume that in the z coordinates here, the laws of physics are exactly what Newton taught us. Let's ask what the laws of physics are now in the primed frame of reference. We have to do this operation over again, but we know the answer. If we differentiate twice here, we get this thing differentiated twice, plus, or minus in this case, just g. The second time derivative of this is just minus g. All right, so the primed acceleration and the unprimed acceleration differ by amount g. And now we can write Newton's equations in the primed frame of reference. Z double dot, if we just transpose the g to the other side, g plus, looks like this. And now we can substitute, and it says that F is equal to m times z prime double dot plus mg. And so we find, as expected, of course, there's nothing here unexpected, that in the primed frame of reference, it looks like, oh, do I have something wrong? Somehow I think I have the wrong sign. Minus g. Must be minus g. What did I do? Did I do something wrong? Z prime is it? Z double dot is Z double prime dot plus G. Is that right? Yeah. Okay. Right. Oh, sorry. Okay. It's fine. Right. I want to shift it to the other side of the equation, of course. Minus mg on the other side of the equation. Why do I want to shift it to the other side? Because I want to make it look like a Newton equation. Mass times acceleration is equal to something, and that something I call the force in the primed frame of reference. And you notice, as expected, the force in the primed frame of reference has an extra term, a sort of fictitious term, which is just the mass times the acceleration of the elevator. Now, what's interesting about it, of course, what's interesting about it is it looks exactly like the force law of a particle at the surface of the Earth or at the surface of any kind of gravitating system, uniform gravitational field. It looks like a uniform gravitational field, but let me spell out in what sense it looks like gravity. The special feature of gravity is that gravitational forces are proportional to mass. That has a deep implication. The deep implication is, since the equations of motion are F equals ma, and if the force itself is somehow proportional to mass, then the mass cancels, and the acceleration and the total motion of the system, of the object, doesn't depend on its mass. That's a characteristic of gravitational forces, that an object moving in a gravitational force, small object in gravitational force, its motion doesn't depend on its mass. An example, for example, would just be the motion of the Earth about the Sun is independent of the mass of the Earth. If you know where the Earth is at some instant and you know how fast it's moving, then you can predict how it moves without regard of what the mass is. All right, so here's an example of a fictitious force, if you like, if you want to call it that, mimicking the effect of gravity. I think most people before Einstein considered this largely an accident. Just, people knew it. They certainly knew that the effect of acceleration mimicked the effect of gravity, but they didn't pay much attention to it. It was Einstein who said, look, this is a principle. This is a deep principle of nature that gravitational forces cannot be distinguished from the effect of an accelerated reference frame, from the effect of looking at physics in an accelerated reference frame. That physically they are the same thing, and they are indistinguishable. Now, we're going to have to discuss that a little bit, whether we really believe that quite in as much detail as I said. But before we do that, let's draw some pictures of what these various coordinate transformations look like. Let's first take the case where L is just equal to Vt. L equals Vt, that was x prime is equal to x minus Vt, or z prime. Did I say x? Z, I mean. Z. Z prime. All right, here is vertically I plot time, horizontally I plot z, and that's z, not z prime. And let's put in some guidelines. Here's, of course, the vertical axis is z equals 0. Here's z equals 1. Here's z equals 2, and so forth. Here's z equals 3. Now let's put in, and here, of course, is z equals 0. Now let's put in z prime equals 0. Z prime equals 0 is the same as z equals Vt. Z equals Vt is a trajectory that moves upward to the right and looks like this. How about z prime equals 1? Z prime equals 1 looks like this. Z prime equals 2 looks like that. Z prime equals 3 looks like this. And this is the nature of the coordinate transformation that relates the primed and the unprimed reference frame. Every point has a coordinate t and z, has a pair of coordinates t and z, and also an x, incidentally, but I've dropped it. a t and a z and a y, and the z prime and the z coordinates are related in this way. Also, t prime is equal to t. Let's put in t prime equals t. So that's called a linear transformation. Straight lines go to straight lines. Not surprising, since Newton tells us that particles move in straight lines in an inertial frame of reference. And what is a straight line in one frame had therefore better be a straight line in the other frame. They move in straight lines not only in space, but in space-time. Okay, now let's do the same thing for the accelerated coordinate system. Where is it? Z prime is equal to z minus 1/2 gt squared. So let's look at z prime equals 0, the trajectory of the origin of the z prime coordinates. That's the same as z equals 1/2 gt squared. That's a parabola. Okay, it's a parabola lying on its side. Why? Because because it's a parabola lying on its side. So it looks like this. That's the trajectory. It's accelerating. It's going faster and faster and faster. Incidentally, I could run this back into the past. A uniform acceleration upward forever and ever would correspond to something moving downward, decelerating, and then going up and going back up. Okay? So if I wanted to continue this to make a full uniformly accelerated trajectory out of it, it would look like this. Z comes down and then goes back up and down. All right, what about z prime? This now is z prime equals 0. What about z prime equals 1? Well, that's just a shift of this parabola, which I always have trouble drawing. It always gets cramped somehow. Z prime equals 2 looks like this. These parabolas seem to be getting narrower and narrower, but that's only because I'm not good at drawing them. Each one is just shifted relative to the previous one by 1 unit. And the point is, of course, not surprisingly, straight lines in one frame are not straight lines in the other frame. They're curved lines. And so one would say, did I write the wrong thing here? That was, yeah, 1/2 gt squared. Gt squared over 2. That's the coordinate system here. This is a curvy linear coordinate transformation. So something Einstein understood very early is there's a connection between gravity and curvy linear coordinate transformations of space-time. That special relativity was all about linear transformations, transformations which took uniform velocity to uniform velocity. Lorentz transformations are of that nature. Take straight lines in space-time to straight lines in space-time. But if we want to mock up gravitational fields through their effect on, through the effects of acceleration, we're really talking about transformations of the coordinates of space-time, which are curvy linear. And so what Einstein realized is that if you, yeah, okay, I said it, I don't need to say it again. Let me just give you one example. This sounds extremely trivial, doesn't it? It sounds very trivial. We all knew it. And I think every physicist, when Einstein said it, probably also knew it and said, oh, yeah, oh, well, big deal. But Einstein was very clever. He realized this could answer questions that nobody knew how to answer. So let me give you one example. I've used this in this class a number of times, but we're going to do it anyway. An example of a question that Einstein answered this way. The question had to do with what is the influence of gravity on light? Now, at that time, in around 1907 or something, when Einstein first thought about these things, even 1905, he started thinking about gravity. Most physicists would have answered, there is no effect of gravity on light. Light is light, gravity is gravity. A light wave moving near a gravitating object just moves in a straight line. That's the law of light, that it moves in straight lines, and there's no reason to think that gravity has any effect on it. But Einstein said, no. If it is true that this is a principle, the equivalence between acceleration and gravity, then gravity will affect light. And the argument was very simple. Again, one of these arguments which you could almost explain to a child. Let's start out with a light wave, a light beam, whatever it is. This is x now, not z. Z is vertical. Let's start out with a light beam that's moving horizontally, starting out at t equals 0. At t equals 0, the velocity of the elevator is 0. At t equals 0, the velocity begins to build up from t equals 0. At t equals 0, the two frames of reference are matched. They're both at rest relative to each other at t equals 0. And a flashlight beams a beam of light this way. Okay? Now, in the unprimed frame of reference, the C frame of reference, we know how the light wave moves. Or at least Einstein said, in the frame of reference without any gravity, because there is gravity on the surface of the Earth. What am I talking about? We shouldn't be, for our purposes now, the Earth is so light that it doesn't make any gravity of its own. All of the gravity is due to the acceleration. All of the gravity is due to the acceleration, or the apparent gravity. And so we said, well, in the frame of reference at rest where there is no gravity, we know what the light wave does. The light wave just moves horizontally across here. All right, we can write down, again, I want to write the equations just to illustrate. What is the equation of this light beam? Well, it's first of all x, horizontal, is equal to the speed of light times the time. Let's make this distance here L. Different L. X is equal to ct. That's how light moves. Okay? And also, z is equal to 0. Z doesn't change in the unprimed frame of reference. It just moves horizontally. Okay, so that's the equation of the light beam. But now let's plug in the primed frame of reference. In the primed frame of reference, z is equal to z prime plus tg squared. So we have that z prime plus gt squared over 2 is equal to 0. That's the equation of the light beam. X is still just equal to ct. And that's it. Okay? So here we see what the light beam is doing in the primed frame of reference, namely it's moving on a curved trajectory. If we were to calculate its vertical component of velocity, we would discover it looks like that. All right, I say in the primed frame of reference, gravity is pulling the light beam down. You say, no, it's just that the elevator is accelerating upward, and that makes it look like the light beam moves on a curved trajectory. And Einstein said they're the same thing. This proved to him that the effect of a gravitational field on a light ray was to cause it to curve, was to cause it to bend. Right? And that was something that no other physicist knew at the time. So, clever. Okay, but up till now, what we've learned, the thing that I want to abstract out of this, is that it's interesting to think about curvilinear coordinate transformations. When you do think about curvilinear coordinate transformations, Newton's laws do change, or the form of Newton's laws change. And one of the things that happens is apparent gravitational fields materialize that are physically indistinguishable from ordinary gravitational fields. Well, are they really physically indistinguishable? Not really. let's talk about real gravitational fields, namely gravitational fields of gravitating objects like the sun or the earth. Here's the sun or the earth, and the gravitational acceleration doesn't point vertically on this blackboard, it points toward the center. So there's gravitational fields pointing radially inward. It's pretty obvious that there's no way that you can do a coordinate transformation like this which will remove the effect of the gravitational field. Yes, if you're in a small laboratory here, and that laboratory is allowed to simply fall toward the sun, or whatever it happens to be, then you will think in that laboratory that there is no gravitational field. But there is no way globally to introduce a coordinate transformation which is going to get rid of the fact that there's a gravitational field pointing inward toward the center. If you make a transformation like this, it might get rid of the gravity over here for this infalling object, but the same transformation on this side will just increase the gravitational field. So, no, there is no way to get rid of it. We know there's no way to get rid of it. And one way to understand why you can't get rid of it is because if you think of an object which is not very, very small in this gravitational field, let's suppose it's okay. My favorite 2,000-mile man. The 2,000-mile man is falling in the gravitational field. Well, let's just start him out differently first. Let's start him out falling feet first. Okay. Because he's large, not the point mass, the different parts of him feel different gravitational fields. The further away you are, the weaker the gravitational field is. And so his head feels a weaker gravitational field than his feet. Okay? His feet are being pulled harder than his head. Guess what? He feels like he's being stretched. Right? If he's freely falling, he can't distinguish this from a stretching feeling, but he knows that there's a gravitating object there. That gravitating object cannot be removed by, and the sense of discomfort that he has cannot be removed by going to a falling reference frame. These are, of course, tidal forces. Tidal forces cannot be removed by, if he's very small, of course, if he's very small, then his feet and his head feel the same gravitational force. What happens if he's sideways falling? Well, if you look at this gravitational field, you can easily see that there's a component of the gravitational acceleration, gravitational force on his feet, which is pointing upward here, just because this vector has an upward component, and this one has a downward component. So he'll experience a sense of compression. And that sense of compression is, again, not something that you can remove by any coordinate transformation. It's an invariant fact. Being squashed to death is an invariant fact. It's not something you can make go away by doing a coordinate transformation. So it is not true that gravity is equivalent to going to an accelerated reference frame. Einstein, of course, knew this. I mean, he was no fool. He knew this. So what he really said is that small objects for a small length of time cannot tell the difference between gravitational field and an accelerated frame of reference. But that then raises the question, if I present you with a force field, for example, the force field associated with uniform acceleration is just a vertical force field pointing downward and uniform everywhere. It's a consequence of this nonlinear coordinate transformation. But nevertheless, it behaves for an observer using these coordinates like a gravitational field. But with other kinds of coordinate transformations, you can make the gravitational field look more complicated. Other kinds of coordinate transformations, for example, transformations which affect the x-coordinate also, for example, they can make the gravitational field bend toward the x-axis. Supposing you simultaneously accelerate along the z-axis while oscillating back and forth in the x-axis. Your frame of reference is oscillating backward and forward along the x-axis and accelerating along the z-axis. What kind of gravitational field do you see? A very complicated one. It's got a vertical component and it has a time-dependent oscillating component along the x-axis. So by appropriate coordinate transformations, you can make some pretty complicated apparent gravitational fields. If I tell you what the gravitational field is everywhere, how do I determine if it's just a sort of fake gravitational field coming from doing a coordinate transformation using a frame of reference with various kinds of accelerations in it, or is it a real genuine gravitational field? Well, if it's just Newtonian gravity, there's an easy way. You just calculate the tidal forces. You calculate whether that gravitational field will have an effect on an object which will cause it to squeeze and stretch. If it does, then it's a real gravitational field. If you discover that that gravitational field has no such effect on any object, no tidal force, no tendency to distort a freely falling system, a system which is in free fall, then, and no matter where it is, drop it here, drop it here, drop it here, wherever you drop it, if it doesn't have such a tidal effect, then it's not a real gravitational field.
Question.
Yeah.
Seems like you could simulate the tidal effect. For example, put a rocket engine and speed in his head and have a more powerful one.
What's that again?
It seems like you could simulate even the tidal forces.
No.
Suppose you had a rocket engine on his feet.
Hmm?
It has a greater thrust than one on his head.
It doesn't matter. In the unprimed frame of reference, there is no gravitational field. So there's no way that there can be a distorting effect on you or anybody else, because you can calculate it in the unprimed frame, and there was no gravitational field. So the question then is, how do you know when it's possible to make a coordinate transformation that removes the gravitational field? How do you know when it's just an artifact of coordinates, or when it's a real physical thing due to some gravitating mass, for example? That's a question.
Question?
Yeah.
Just, this is intuition and it's probably way off the mark, but in a situation where you have one body creating a gravitational field, what happens if you go to an angular coordinate system?
In terms, right, good. Of course, we don't even need to have a gravitating object there. We could have no gravitating object and go to polar coordinates. I think that's what you're talking about, right? Okay? Now, that means we have two coordinates, r and theta. Supposing we didn't know that these were polar coordinates. All we knew was there was a coordinate r and a coordinate theta, and I told you how a particle moves theta and r as a function of time. How would the particle move, meaning to say, what would theta of t and r of t, how would they behave as a function of time? And I would plot that. I would look at it and see what kind of motion the particle had, theta and r as a function of time. So let's guess. Let's suppose a particle moves across here. What happens to r? Well, r starts decreasing, 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 and incidentally, theta is increasing. Well, I take it back. It's decreasing. It's going this way. But theta is evolving, and meanwhile, at the same time, r is decreasing, 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 till it gets to here, and then it goes back out. This person who was using polar coordinates and didn't know it would say there must be a repulsive force repelling the particle away from r equals 0, and that repulsive force is, we know what it is, it's centrifugal force. It's the centrifugal force of having some angular momentum, but nevertheless, if you didn't know where you got these coordinates from, you would say, my God, look what's happening. R is coming in and going back out. Effectively, there is some kind of repulsive force. That repulsive force would be proportional to the mass. Centrifugal force is proportional to mass. And you say, this is an interesting situation. There's a radial outward gravitational field. In every respect, it would behave as if there was a gravitational field pushing things outward from the center. Maybe you might think there's some matter out there. That wouldn't be right. But a ring of matter out there pulling it, that wouldn't be right. But you would have discovered a force on an object which pulls it out, and it pulls it out proportional to the mass, and you would say, I found something new. I've discovered kind of anti-gravity pulling me away from the center. So basically, any kind of coordinate transformation you do, if the coordinate transformation is nonlinear, in other words, doesn't take lines to lines, will produce effectively some kind of effective fictitious force. What are the fictitious forces here? Centrifugal force, Coriolis force, all those kinds of things. And they all have the character of gravitational forces. But again, somebody in a small laboratory moving along here would not experience any sort of distorting effect, clearly, because we can always study it in the inertial frame, the linear, the nice linear reference frame, and there are no distorting effects. So it follows that by a coordinate transformation, you can get rid of these fictitious forces. The question is, if I just give you a gravitational field, how do I know if I can get rid of them? Well, the answer is calculate things like tidal forces. But, yeah.
Isn't that only true if you're dealing with two bodies? If you assume that there exist, more than two bodies, you could have one that's below the trajectory, another that's in the same position above it, and a third that's on the side.
Say it again? No, I don't understand.
I think the analysis that you gave only holds if you've got two bodies.
Yeah.
So if you had three bodies, for example, one that's above the trajectory, the same distance as the point you have below it. So it's a mirror image that would be up by the t that you've got in x equals ct. Yeah, it cancels out the other one. And then if you had a third that's where the big sun is, for example, the two that offset one another would cancel out.
Here, there's nothing making a gravitational field here. This is just an artifact of a coordinate system.
Now, I'm trying to give you I guess it's a four-body example, where I don't think you have the tidal forces.
If you have four bodies making a gravitational field, well, there certainly will be tidal forces for something falling in over here.
As it's passing, I'll talk to you first.
Yeah, I mean, if there are four objects over here creating a gravitational field, and one of them, and somebody gets close to one of them, they can forget the other ones, and they'll experience a tidal force. So, what do? You try all possible coordinate transformations. Coordinate transformations means coordinate transformations of space and time, and rewrite the equations of motion and see if you can find a coordinate transformation that eliminates all of the fictitious forces. If you can, then you say there's no real gravitational field there. If you can't, you say, yes, there was a real gravitational field that could not be eliminated. Now, Einstein, yeah.
Pardon my ignorance, but what does it mean to compute tidal forces?
Oh, you take a chunk, a mass of some kind, an object, a crystal, and you put the crystal into the gravitational field and you let it fall, and you ask whether there are stresses and strains on the crystal which squeeze it one way and stress it the other way. Yeah. And these would be detectable things.
So coming back to the centrifugal thing, so let's say our 2,000-mile man is on a merry-go-round.
This is a merry-go-round. Okay, this was not a merry-go-round. This was just a use of coordinates which were not the right.
Centrifugal force,
Right.
right? So, I mean, couldn't you kind of come up with some, like his feet are going to be moving with that centrifugal force, that his head is 2,000 miles away and it doesn't feel it. So don't you end up with kind of something?
No. Okay, no. When I say there is no effective tidal force, I mean for a freely falling object. If you have a freely falling object, it's not being held in place by ropes or pulleys or anything else, it's just allowed to free fall, then no. If there was a carousel rotating, here it is, rotating, and somebody is in free fall, they will appear to move very oddly from the point of view of the person on the carousel, but in the reference frame of the, at rest relative to the Earth, they move in nice straight lines and they feel no tidal forces. So if you calculated the effect of the tidal force in either frame, you would find it zero. In other words, tidal force means effectively distorting stresses on matter that squeeze it and pull it. Simplify it. Does it give you a headache or doesn't it give you a headache? The answer is if you were in free fall, if you're stuck on the carousel, you might get a headache. But you're not stuck on the carousel. You're moving in free fall. You get no headache.
So going back to what you were saying about trying to transform the tidal forces away.
Yeah.
Okay. I'm looking at your little picture of a guy over there.
Yeah.
So if he's facing that direction,
Yeah.
he's going to get squeezed.
Uh-huh.
If he's rotated 90 degrees, he's going to get stretched.
Mm-hmm.
Could you be clever and maybe tilt him at 45 degrees so he gets stretched and squeezed? And
No, wait. No. Let's put it, okay, this is not just a 2,000-mile man. He's also 1,000 miles wide, okay? He gets stretched and squeezed. He gets stretched and squeezed, and there's just simply no way to get rid of it.
You have to look at all directions at once. So somehow.
Right.
I think here you're saying that because the tidal forces, the equivalence principle doesn't hold.
Well, it means it has to be stated carefully. It means it has to be stated carefully. And stating it carefully would say something like, if you take a sufficiently small system, small means such that the gravitational field across it doesn't vary much. If the gravitational field, if it's small enough that the gravitational field doesn't vary between one part of the system and another, that is when the equivalence principle holds with accuracy. Right. Einstein knew all of that. And so he asked himself the question, what kind of mathematics goes into trying to answer this kind of question? Now, the other element that came into it was special relativity. And he knew from the work of Minkowski that special relativity had a geometry associated with it. The geometry had the property that it had a kind of length associated with it. The length was called proper time. Proper time or proper distance, doesn't matter. And I'm just going to remind you about that very quickly. In special relativity, there is an invariant notion of the space-time difference between a pair of points, or a pair of neighboring points, for example. We're taking a rest now from gravity, and we're coming back to special relativity. And the only thing we're going to use about special relativity is that space-time has a geometry. The geometry is the geometry discovered by Minkowski, and it has a length element. A length element means any pair of points with x and t. I'm going to use x and t now. Of course, there's also two other coordinates, but let's concentrate on x and t. And the space-time difference, or distance, between 2 points is called ds squared. Depending on who's writing the equations, they will either write ds squared or d tau squared. And they only differ by a sign. D tau squared is what? Anybody remember? dt squared minus dx squared, yes? Where does the speed of light go into this if we wanted to put it in? Is it dx squared over c squared or dx squared times c squared? I can never remember.
dx squared over c squared.
I think it's over c squared. But we can always get rid of this 1 over c squared by redefining x. Instead of calling it x, call it x over c, and it just becomes x squared then, or just instead of x, x over c. And that in itself is a coordinate transformation. So you can always bring this coordinate interval to this form, this being called proper time. And some physicists like to use the s squared, which is exactly the same, except by sign. It's dx squared minus dt squared. Einstein knew about this geometry, and he realized that this question up there, what kind of are there coordinate transformations which can remove the effect of tidal forces, was very similar to a certain mathematics problem that had been studied at great length by Riemann. Namely, the question of deciding whether a geometry was flat or not. Geometry of a page is flat. The geometry of a hemisphere is not flat, or a sphere is not flat. And he realized that there was a great deal of similarity in the two questions of whether a geometry is flat, whether a space-time has real gravitational field in it, that they were very similar. So let's talk about that a little bit. This minus sign here, Riemann had never dreamt about. Riemann had not thought about geometries which have a minus sign here. He was thinking about geometries which were similar to Euclidean geometry. What's the right formula in Euclidean geometry? I think we want to start with the mathematics of Riemannian geometry. We're not going to spend a huge amount of time on it, but we're going to spend a little bit of time on it. What's the corresponding thing for Euclidean geometry? And now let's just say there are a bunch of x's. This could now be x1. This could be x2. There could be another x3 coming out here. And supposing there's a little interval here characterized by a dx, and let's call it m. M represents whether it's x1, x2, or x3. This is not x1 squared. This is x1, x2, and x3. And if I prescribe for you a set of, in this case, 3 dx's, 3 components of a little shift, what's the distance between these 2 points? And we all know it. It's just Pythagoras' theorem. In any number of dimensions, it's the same. The square of the distance, and let's call it s now, the square of the spatial distance between those 2 points is just equal to dx1 squared plus dx2 squared plus ... however many there are. If the space is 3-dimensional, then there are 3 of them. If the space is 2-dimensional, there are 2 of them. If the space is 26-dimensional, there are 26 of them, and so forth. That is the formula for Euclidean distance on the Euclidean, in a Euclidean space, for the distance between 2 points. Now, Gauss had already understood that on curved surfaces, the formula for the distance between 2 points was more complicated in general than this. Two-dimensional surfaces. And Riemann generalized this to arbitrary dimensions, however many dimensions you have. And what was known from the theory of surfaces is that the right formula for the distance between 2 points, first of all, before we talk about it, let's suppose we have some kind of surface. Curved surface. What we mean by it being curved is not clear yet. But some sort of arbitrary surface that looks like it's curved, no particular shape to it, but we have every reason to think it's got something that we might call curvature. Okay, so the first thing we do with it is we put some coordinates on it. We want to be able to quantify various statements, and so we want to introduce some coordinates onto it. We just lay out some kind of coordinates. We don't worry at all about whether the coordinate axes are straight lines or not, because for all we know, if the surface is a real curved surface, there probably won't even be things that we can call straight lines. So we just lay out some coordinates, and we call them x's. Now we take two neighboring points. Here's two neighboring points. They're again related by a shift of the coordinates. This shift over here is again called dxm. But now for an arbitrary curved surface with arbitrary coordinates, coordinates of arbitrary kind of complexity, the formula is not as simple as this. It has similarities with it, but it looks any geometry, curved or otherwise, and incidentally, this formula also applies to flat geometries if you take curved coordinates. If you take a flat geometry like the surface of the blackboard and you introduce some curved coordinates, some curvilinear coordinates, and you ask what is the distance between 2 points, then in general, the square of the distance between 2 points will be a quadratic form in these little coordinate separations. A quadratic form means that you have a matrix, GMN, M and N could run from 1 to 3, for example, and you just combine together GMN dx dx, just as I've written it here. You've seen these kind of things before. And in general, G will depend on position. Do you know an example? How about distance in how about distance on the surface of the Earth between 2 points characterized by longitude and latitude? You know the formula for the distance between 2 points? You have it's ds squared. Okay, so theta, which one is which? Latitude. Theta is latitude squared. It's the square of the radius of the Earth, d theta squared, and then what's the other one, remember? Well, it's a d phi squared. But it can't just be d phi squared. If you look at the Earth, phi goes this way, theta goes this way. A given amount of d phi can be a big distance if you're near the equator, and the same amount of d phi is a small distance near the North Pole or the South Pole. So there's something else that goes in here which has to do with how close to the North Pole or South Pole you are.
Sine theta?
Yeah. Sine theta squared. Sine theta squared. Not sine of theta squared, but sine squared of theta. Okay. Now here's an example. Here's an example of distance not just being d theta squared plus d phi squared, but having some coefficient functions in front. Now in this case, the interesting coefficient function is sine theta squared. In general, if you use arbitrary coordinates on the sphere, you'll discover a much more complicated formula. But it will always be something which will involve the coordinates quadratically. There'll be d theta squared terms, there'll be d phi squared terms, there'll be d theta times d phi terms. There will never be d theta cubed terms. There will never be things linear. Everything will be quadratic like this. And you'll get some general formula which will involve a matrix and the little separations dx.
Excuse me, if don't we normally measure latitude from the equator, so would it be cosine?
Say it again. We don't measure latitude from the equator. We measure. Sorry, we do measure latitude from the equator. Oh, I'm sorry. Maybe let's see. Yeah, it was probably if you measure latitude from the equator, it would be cosine squared. Is that what you were getting at? Yes. Yeah, that's correct. If latitude is measured from the equator, it's cosine squared. If it's measured from the North Pole, it would be sine squared theta. So, good point. You're right. But the important point is here that the formula for the distance of a differential separation involves functions which sit in front of these quadratic expressions in terms of the differential distances. Okay. And as I said, this is just a very simple example. More general examples would have more complicated functions. There might be a complicated, not necessarily complicated, but a function in front of d theta squared. There might be a function in front of d phi squared. And there may also be a d theta d phi term. All possibilities. All those possibilities are included by saying there's a general matrix here, an Mn matrix, which multiplies the differentials. This, yeah.
Apply with to macro distances, not differential distances, because that formula applies for any distance, right?
Which one? No, it applies for, no, the reason it doesn't apply for arbitrary distances is because you have to specify what point theta you're talking about, and it's only good for distances nearby that point theta. Yeah. Okay, the answer is, in general, for curvilinear coordinates, it only applies. If you want to know, first of all, if you want to know the distance between 2 points, you better define it. And take some arbitrary curved surface. I don't know how to draw it. It's got bumps and hills and all kinds of things in it. What do you even mean by talking about the distance between this point and that point over here? Well, you could mean something. You could mean the shortest distance. You could mean put a peg in here and a peg here and pull a string as tight as you can between the 2 points, and that would define one notion of distance between the 2 points. Of course, there might be 2 answers. One might go around the hill one way and one might go around the hill the other way. So in general, but think about it for a minute. Even if there's only one answer, a unique answer, it's complicated. You have to know the geometry everywhere's in between. You have to know the curves and the hills, not only to calculate the distance, but to know actually where to place the string. If I put another hill in over here, the string would have to go differently. So the notion of the distance between 2 points is a complicated one. But the notion of the distance between 2 neighboring points is not so complicated. For small distances between the points. So basically what you can imagine doing is you're building the geometry out of a sort of a bunch of tinker toy erector sets, tinker toys or whatever, a bunch of little units of given length, and you're piecing them together to form a geometry, if the little pieces that you're putting together are correctly chosen, you might be able to put, it doesn't mean they're all of equal length, but you might be able to put it together into a flat plane. Doesn't mean they're all the same length, in fact, that you can put them back together into a flat plane. But if the pieces are chosen in some particular way, in other words, the lengths of the pieces, which is equivalent to saying that the metric tensor here, this is the metric tensor, if the metric tensor has a particular property, it may be that those pieces can be laid out, little differential elements can be laid out and flattened onto a flat plane. In that case, the geometry is said to be flat. We'll define it more carefully later. But it may also be that the pieces are chosen in a way that you can't lay them out onto a flat plane. There may be, the pieces might be the little elements that you would get by, by sort of triangulating the sphere in some way. Then there would be no way, given their length, given you know what their length is, the length of each one of these, and you know that they can be laid out on a sphere without stretching them, without breaking them, then it's true that you cannot lay them out on a plane. Such a surface is not flat. So the question is, if I gave you the length of each little stick here, without building the thing, how could you tell me whether it's a flat space or whether it's an intrinsically curved space that cannot be flattened out and laid out on a flat plane? Let's say it more precisely. Given Gmn of x, let's give it its name, it's called the metric tensor, as a function of position in some set of coordinates. Keep in mind, there are many sets of coordinates, and in every set of coordinates, the metric tensor may look different, may have different components. But I give you one set of coordinates, and I give you one metric tensor, I tell you what it is. In effect, I've told you the distance between every pair of neighboring points, and I ask you, is this flat or is it not flat? In fact, what do I even mean by asking if it's flat? Yeah.
Measure pi, calculate pi.
That's one way. Yeah, you can do that. Yeah, I know what you mean. That's good. That's very good for a two-dimensional surface. Not so great for higher dimensional surfaces. Yeah, that's right. That's one way of doing it. Actually, that's not so easy to do with these differential little things here, because they're so small that the deviation from pi is going to be higher order. But yeah. All right, so what's the mathematics of taking a metric tensor and asking if the space is flat? Now, what does it mean for it to be flat? What it means to be flat is that you can find a coordinate transformation, a different set of coordinates, in which the interval, the distance formula, is just the x1 squared plus the x2 squared plus the x3 squared, as it would be in Euclidean geometry. That's the definition of a flat space. The space is flat, not if Gmn is just a bunch of zeros and ones, as if it were just the Pythagorean theorem, but if a coordinate transformation can make it look like that. So in that sense, it has a vague similarity. It turned out not to be a vague similarity at all, a very close parallel between the question of whether you can find a coordinate transformation which removes gravitational fields. Question is, can you find a coordinate transformation which removes the curvy character of the metric tensor here? All right, in order to answer that question, the geometric question here, we have to do some mathematics. And the mathematics is central to relativity. We cannot get away without doing it. You cannot understand relativity without it. And the mathematics is tensor analysis. Tensor analysis and a little bit of differential geometry. It's annoying. It's annoying because it's got all these indices floating around. and different coordinate systems. So it's mildly annoying, but once you get used to it, it's really very simple. It is really, really simple. And it was actually made simpler by Einstein, by the famous Einstein summation convention, which means you didn't have to write summation symbols all over the place.
Question?
Yeah.
Yeah, going back to that distance on the sphere, the equation where it's cosine of whatever it is, that assumes that that little interval is flat, otherwise it's...
Yeah, that's right. We assume that small enough. Yeah, that's exactly right. In both Riemannian geometry and Gaussian theory of surfaces, it is always assumed that if you look at a small enough piece, that a small enough piece looks flat. The technical statement is a small piece located at some point can be well approximated by the tangent space. The tangent space would be the flat tangent to the surface.
But it's not flat. They assume it's flat, but it's not flat. So that equation is
It's a question. Yeah, that's right. But it's a question of orders of differentials. It's a question of orders of differential. Remember, differentials aren't really lengths. They're limits of small lengths. And they're defined in such a way that the square of a small thing is 0. So there is a technical mathematics to small differentials.
So is there a constraint that the function has to be continuous?
Yeah.
Because if you take 2 points at the edge of a crevice,
Yeah.
it just, geometry matters a lot in that case.
Depends on what you mean by a crevice. Yeah, no, you're right. No, the metric tensor can always be taken to be continuous. It's often derivatives of the tensor which are not continuous. But I don't know what a crevice means. A crevice does not mean a crease. That's, of course, a crease. This space here is as flat as this space. In fact, it's exactly the same space thought of in terms of differential geometry. The distance, all right, let's be careful. Let's say exactly what we mean. The distance between any 2 points on here, between 2 neighboring points, doesn't mean the distance between these points if you go through the page. Right? It means the distance in the surface. The distance in the surface, and that distance between these 2 points doesn't depend on whether you fold the page or not. It's exactly the same with the page folded as with the page unfolded. The right terminology is we're interested in the intrinsic geometry of the page. The intrinsic geometry means those aspects of the geometry which only depend on what's going on inside the surface and not how the surface is embedded in 3 dimensions. These are different embeddings of the same surface, right? All sorts of different embeddings of the same surface. But the intrinsic relationships between the points on the surface are independent of how we bend the surface. So we're talking about intrinsic geometry, geometry that would be measurable by a little creature that only gets to move around on the surface and doesn't get to look out of the surface. Yeah.
What if we try diagonalizing the metric?
What about diagonalizing it? Yeah. You can't diagonalize, in general, you can't diagonalize it everywhere simultaneously. But diagonalize it, you mean find a set of coordinates that diagonalizes it. Yeah, you can do that at a point. At any point, you can diagonalize it, but you can't diagonalize it everywhere simultaneously. Right, that's the point. That's very much the point. So you can't tell by looking at a point whether a surface is flat. Right, looking at a point, it'll always look flat.
One more question. Could you say that again? The determination of whether space is flat is equivalent to determining whether there's a coordinate transform that takes an accelerator frame to a...
We're dropping now the question about gravity for the moment. I started by explaining to you that there's this mathematics problem of deciding how to find out if there's a gravitational field or if the gravitational field can be removed by coordinate transformation. Now we're talking about a problem that sounds similar, and in fact is similar. How do you tell, given a space, whether it is flat? How do you, and the answer is you look for a coordinate transformation which turns GMN into what? What's the GMN for Cartesian coordinates?
Scalar?
It's what?
Scalar?
It's all the diagonals one way.
And that would mean
Identity.
the identity matrix. Yeah. Or the Kronecker delta symbol, yes? Everybody remember the Kronecker delta, delta Mn? This is the formula for the interval in Cartesian coordinates for a flat geometry. Remember what delta Mn is? Delta Mn is just a matrix, diagonal matrix, everywhere is equal to 1, off diagonal, everywhere equal to 0. Okay? So what we would say is that flat space in Cartesian coordinates, the metric tensor is just the Kronecker delta symbol. In curvilinear coordinates, that's not true. In curvilinear coordinates, this could be more complicated. So I give you a metric. I give you a metric tensor. And I ask you, can it by coordinate transformation be reduced to this? If yes, the space is called flat. If no, the space is called curved. Of course, a space could have some portions which are flat. And on those portions, it could be that there's a set of coordinates where in that region, the metric tensor can be chosen to be the Kronecker delta. But it's called flat if it's everywhere is flat. Everywhere is flat. All right, so that's a mathematics problem. Given a GMN of x, how do you decide if there's a coordinate transformation which will change it into the Kronecker symbol? To answer that, we have to understand better how things transform when you make coordinate transformations. And that's the subject of tensor analysis. This analogy between tidal forces and curvature is not an analogy. It's a very precise equivalence that in general theory of relativity, the way that you diagnose tidal forces is by calculating the curvature tensor. The way you define a flat space is a space where the curvature tensor is 0 everywhere. And so it's a very precise correspondence that gravity really is curvature. But we'll come to it as we get to it. Okay, so obviously the first question we would like to ask in trying to determine whether we can transform away GMN of x and turn it into the trivial delta Mn of x, the first question to ask is, how does GMN of x transform when you change coordinates? So as I said, for that we have to introduce notions of tensor analysis, which are rather easy. Sometimes they're a bit of a notational nuisance because of all the indices, and you can get confused by them, but I hope you won't. Okay, so let's begin with a simpler thing than GMN of x. Let's just start. Let's suppose there are two sets of coordinates. There's the set of coordinates xm, and I could call the other coordinates x prime, but then I'm going to have a horrible notation where we'll have x prime m. Oh boy, it looks like x prime 1 would be x11. Let's keep away from that. Let's not do that, and let's call the two sets of coordinates x and y. It's not x, y, z type y, it's just x1, x2, x3, x4, however many, and y1, y2, y3, y4. Two sets of coordinates, x and y, and of course they're related because if you know the coordinates of a point in one set of coordinates, then in principle you know where the point is, and therefore you know its coordinates in the other coordinate system. So we might write that x, the coordinates xm, are functions of y, and what I mean by functions of y here is I mean functions of all of the components of y. And likewise, ym are assumed to be known functions of the x's. Ym of x means ym of x1, x2, x3. I just don't want to write all of the labels in there. We have two coordinate systems, each one being a function of the other. And let's ask the question how these differential elements here transform. In other words, given dxm, that means given a pair of points neighboring to each other, and a little dxm, differential distance between them, differential separation between them, what's the corresponding differential separation of the y coordinates? This is the differential separation of the x coordinates. What's the differential separation of the y coordinates? Right? A little bit of calculus will tell you the answer. dym is equal to the change in y, m, when you change any one of the x coordinates by a little bit. Let's call it dxp times dxp. Now, what does this mean? First of all, this formula is summed over p. This just says that the change in y, some particular component, is the sum of changes in y if you change x1 a little bit times a change in x1, plus change x2 a little bit times a change at the x2, and so forth. All right, so this is a standard calculus formula, the differential change in a quantity when you change the coordinates from one set of coordinates to another. Now, right here we have the first example of the transformation of a tensor. dx and dy, what do they represent? They represent a little vector, an infinitesimal vector in this sense, but they represent a little vector, a vector going from one point to a neighboring point, located at some point in the space, a vector. This is the transformation properties of the components of this vector. This is the transformation properties of the components of what is called a contravariant vector. A contravariant vector simply means a thing which transforms like this. I will now give you the definition of a general contravariant vector. It's a thing that has components, Vm, which in the primed frame, when I speak about the primed frame, I'm speaking about the y frame, the y coordinates. Let's go back for a second. What are we talking about here? We have two sets of coordinates. Let's just draw one set of coordinates. And we have a little vector someplace. And we are interested in the components of that vector along the axes prescribed by the coordinates, whatever those coordinates have to be. We're interested in the components of the little infinitesimal vector along specific axes, the axes which are locally the axes associated with the coordinates. those are these dy's and dx's. If I change coordinates, at this point here, there might be some other coordinates. And the components of exactly that same vector in the new coordinates will be different. It's the same vector, but different components. Why? Just because the axes are different. Okay, so this is telling you, if I tell you what the dx's are for a specific vector over here, this tells you what the dy's are. This is the transformation property of the components of a vector.
Quick question.
Yeah.
On your diagram with those curved coordinates, each one of those lines, does that represent all of the other coordinates being held constant and you're just varying
Yes.
one
Yes.
component?
Yes. That's right. That's right. Those lines represent lines. They represent surfaces, strictly speaking. They represent surfaces, strictly speaking. Lines are surfaces of constant coordinate of some kind or another. But on a two-dimensional surface, they're just lines. Yeah, so if you change coordinates, you change the components of a vector, even though you're not changing the vector. The vector is a very definite vector. You're changing its components because you're changing the coordinates that you're relating the vector to. Okay, a thing which transforms in this way, and I will now write it, in the primed coordinates, Vm is equal to dym by dxp times Vp. This is the pth component of a vector. This is the mth component of vector in the primed reference frame. This is the transformation property summed over p. This is the so-called transformation property of a contravariant vector. We'll see why we have to call it I don't know why it's called contravariant as opposed to something else. But we'll see there are two different kinds of vector indices. Okay, so there are many, many things which would transform in this way. For example, if this were just ordinary space of some sort, and we were talking about the velocity of a particle on the surface. Let's suppose this was a surface. And we're talking about the components of velocity along the surface. The components of velocity along the surface would transform in this way. If you knew the velocity components in one set of coordinates, this would tell you what the velocity was in the other set of coordinates. So this is an example of transformation properties. Now, the first thing that one of Einstein's great discoveries was that you can leave out the summation sign here, and people will figure it out by looking at the equation and say, oh, wait a minute, this side has no p, this side has p's, this equation doesn't make sense, what do I do with it? Well, it really means you sum over p. Whenever there's a repeated index like that, that doesn't make sense from the left side of the equation and it appears on the right side of the equation, it really stands for summation over that index.
Quick question?
Yeah.
Here you're assuming coordinates that transform according to the rules, but could there be other coordinates that don't transform that way?
I haven't assumed anything. I've just assumed there are two sets of coordinates which are functionally related to each other. That's all. And you're assuming some things. You're assuming a degree of continuity. You're assuming that the functions are smooth enough that they can be differentiated. But aside from that, no, we're not making any deep assumptions about the nature of these coordinates. All right, so this is the transformation property. Let's write it down over here, put it up in the corner. Contravariant transformations. Contravariant vectors are defined. They're defined by their transformation properties. And here it is. The prime m, let's write, is equal to dym by dxp vp. This is v in the unprimed coordinates. This is in the primed coordinates. Y is really the primed coordinate, and x is the unprimed coordinate. As I said, I've called it y instead of x prime just to avoid a a miserable notation with primes next to indices. Okay, this is contravariant vector. Good. Now let's talk about covariant vectors. Another creature, completely different. The gradient. The gradient. If you have a function, let's suppose we have a function. Let's think of it as a scalar function, a function that doesn't have to be transformed. It just has some meaningful value at every point of space. Let's call it S. Then the gradient is also a kind of vector. What is the gradient? The gradient is the set of things, the set of components, derivative with respect to xm of S, where S is some scalar function. Everybody know what a scalar is? A scalar is a thing which doesn't transform, it just has a value at every point. It has a well-defined value at every point. It could be something like the temperature, it could be something like the Higgs field, whatever it is, something which doesn't have components because it's just a number at every point. The gradient of a scalar is also a vector. It's the gradient vector. But it doesn't transform the same way as the dx's. It doesn't transform as a contravariant vector. It's easy to figure out how it does transform. Let's ask, supposing we know this, can we compute what ds by dy, let's call this p here, let's call this p just for fun. Can we compute what the derivative of s with respect to the y's is? Again, it's an elementary calculus problem. The elementary calculus problem is that the change in s, when you change ym a little bit, keeping the other ones fixed, keeping all the other components fixed, is just derivative of s with respect to x times the derivative of xp with respect to ym. What is this rule called? It's some version of a chain rule. That if you want to know how something changes when you change y a little bit, then you first change x1 a little bit and see how much x1 changes when you change y. Change x2 a little bit, see how much x2 changes when you change y. Do the same thing with x3. And again, this means sum over p. I'm not going to write the sum over p anymore. If there's a repeated index on this side, which just doesn't show up on this side, it must mean that it's summed over. So that's Einstein's summation convention. It made life a lot easier for printers and for other publishers who didn't have to put in summation signs all over the place. All right, so let's see, how does this compare with this? This is the prime. This is now some primed variable. This is now in the primed coordinate system. Let's call the gradient here, let's call it w. This is w sub m on the left, w sub m on the left-hand side. Notice I'm putting the index downstairs here. This index was upstairs. Here I'm putting this one downstairs. You'll see why. You'll see that this makes nice sense in a minute. This index is downstairs. Why is it downstairs? Well, it's downstairs. All right, ym is equal to, now this is the xp by dy ym, this is the primed y, this is the primed gradient, derivative with respect to y, that's equal to the xp by dy m times, now what is this thing over here? This is w sub p, it's the unprimed gradient. It's the unprimed gradient because it's differentiated with respect to the unprimed variable. That's wp over here. Here we have the xp by dy m, and here we have the primed gradient. This is different. It's different, it's similar. The primed contravariant vector has components proportional to the unprimed, but with dy by dx. Here we have dx by dy. Okay? dy by dx, dx by dy. A thing which transforms this way. Transforms means that if you can calculate it in one frame, here's how you calculate it in the other frame. A thing which transforms this way is called a covariant vector. So let's put that in here. Objects which transform this way. Now, I can tell you right now that if you're uncomfortable with this and it doesn't ring a bell and it doesn't feel good to you, this is what you need to understand. It really is completely central to the entire subject of general relativity. Where the indexes go, where the indices go, and how they transform. That's what relativity is all about. It's all about the transformation properties of different kinds of objects. A vector is a special case of a tensor. Tensors are things which are defined by the way that they transform. The way that they transform means the way that they change when you go from one set of coordinates to another. It is, so that is what you have to get down if you want to understand general relativity. There's transformation properties of vectors and other objects. So here are the two, covariant and contravariant.
Excuse me, is that partial of xg partial of y?
M.
Is that a lowercase m? Or
Yeah, lowercase m. Yeah, all right. And they just label the different coordinates. And notice there's nowhere in here which I've told you whether this is two-dimensional space, three-dimensional space, four-dimensional space, could be anything. The dimensionality of the space, of course, is the number of different components. P could run from 1 to 4, it could run from 1 to 3, it could run from 1 to 2. But the formulas are exactly the same in every dimensionality. The formulas for transformation properties. Okay, so this is the notion of covariant and contravariant vector indices, vectors. Let's talk about tensors now, or more complicated kinds of objects. This is obviously complicated enough, but we have to go a little, yeah.
What's the connection with the contravariant and covariant vectors?
Nothing yet. Nothing yet. Nothing yet. They're two different kinds of objects. Now later on, we will find ways of taking any covariant object or any contravariant object and constructing from it a covariant object in a kind of one-to-one correspondence. Okay, that's later. But for the moment, they're just different kinds of objects. Basically, the gradient operation and the, this is characteristic of velocities. This is characteristic of gradients or rates of change of things. So for the moment, they're different things.
Question?
Yeah.
The last time, we basically, if I remember correctly, said when we lower the index, we change the sign at the time. Did we forget?
Well, at the moment, we're just dealing with Euclidean space. We're not dealing with relativity. Yeah, just coordinates in ordinary space. We'll come to that sign change when we yeah.
So when you say we're talking about two different kinds of objects, that means we should not be thinking in our heads, oh, these are the covariant components or the contravariant components?
Well, if you know what the connection is, yes, you can. But at the moment, no. Right. We'll find a way to relate every covariant to a contravariant, and then you can think of basically a vector as having either covariant or contravariant representation. But then we'll come to that. Okay. All right, next step. Let's talk about tensors with more than one index. Now, the pattern for tensors of more than one index is just to imagine products. Let's suppose there are two contravariant vectors. Let's start with two different contravariant vectors. Let's call them V, and I suppose I've already called it, and U. Two different ones. And let's put them next to each other and take the M component of V and the N component of U. And let's just call this TMN. I think just for the sake of argument, let's suppose we're talking about three-dimensional space, so that M and N run over from 1 to 3. How many components does VM have? 3. Right. How many components does UN have? 3. How many components does TMN have? 9. Right. Notice it matters whether you put it MN or NM. They're different things. VMN is not the same as VNM, if you know what I mean. So where you put the index here matters. But there's a thing called TMN. TMN is a special case of a tensor of rank 2. Rank 2 means that it has two indices like that, and in this case there would be 9 components. In 4 dimensions there would be 16 components, in 2 dimensions there would be 4 components, and so forth. Okay, how does this thing transform? For example, VM and UN could be the components of these vectors in the unprimed frame of reference. I think I want to, yeah, it's called TMN. So this is T in the unprimed frame of reference, and it's composed out of the components of the individual vectors also in the unprimed frame of reference. Well, since I know how the individual components transform, I can tell you how T transforms. So let's see if we can figure out what T prime MN is. Well, first of all, what is V prime? V prime is over here, and it's equal to dym by dxp times Vp. That's Vm, or the primed version, V prime M. Now what about U prime? U prime, same kind of formula, partial of yn with respect to, let's call it xq, uq. Just look at the two pieces separately. The ym by dxp times vp, that's v prime m, v prime m. The yn by dxq times uq, that is u prime n. So I've just done this operation, same operation, but I've done them on the separate components. But now I can just take this apart, put this Vp over here, and what is this object? What's VPUQ? It's just TPQ in the unprimed frame. So I found out how T transforms. Not surprising, because it was just a combination of two vectors, and basically each index here transforms with a dy by dx type thing here. Okay. Anything which transforms like this is called a covariant tensor of rank 2. For each index, there's an operation. For the m index, there's an operation, dym by dxp. For the n index, there's a dyn by dxq, and then you multiply it by tpq. This is contravariant. This is a tensor with two contravariant indices. Okay. All right. If there were more indices up here, mn, I don't know, r, pq, what comes after q? But I've already used R. MN L. LMN. What comes before P? No, that's no good. PQR. And what am I missing? I'm missing DYL by DXR. This would be the transformation property of a rank 3 contravariant tensor. What kind of things are there which are these kind of tensors? Many, many things, but in particular just products of vectors, products of components of vectors. We're going to see that this metric thing here is a tensor, but it's a tensor with covariant indices. So let's ask how things with covariant indices transform. Here is the way a single covariant index transforms. Let's go back. And take the product of two of them. Again, two different covariant tensors. W prime m times W prime n. With covariant. Covariant means that they're downstairs here. How does this object transform? Well, we know how the individual, not W, give me another letter. Z, okay. Not coordinate Z, but component Z. All right, here's the rule. W prime m is equal to dxp by dym times WP. Z prime n, same game, dxq by dyn times zq. All right, so here I've discovered now a new transformation property of a thing with two covariant indices, two downstairs indices. Let's call it TMN. It's a different object, just using T for tensor. Tensor with two lower indices. It transforms this way. So this is transformation property of a thing with two covariant indices. I'll leave it to you to try to guess what the transformation might be if there's one upper and one lower. We're not going to use it tonight. But let's, oh, we're about finished. Well, I think I'll just do one more simple thing here before we finish. The question is how the metric tensor transforms. And this is easy. Supposing we want the same interval except expressed in terms of the y coordinates. All we have to do is write that ds squared is equal to gmn of x. I'm simply rewriting what I have here. But then what is dxm in terms of y's? It's partial of xm with respect to y p, let's say, times dyp. You know, I'm getting really tired. I think we're going to do this next time. We're going to do this next time. We're going to do this next time. The point, however, is when we work out the transformation properties of G, we'll find out that it's tensor. It's a tensor with two covariant indices. And then comes the question, given that this is the transformation property of G, can we or can we not find a coordinate transformation which will turn GMN into delta MN? That's the mathematics question. It's a very hard mathematics question in general, but we'll find the condition.
For more, please visit us at stanford.edu.